Determinants of economic growth. In this section, we will talk about the various factors such as capital, labor, technology, etc., which contribute to economic growth. Now, the big context is as follows. As a financial analyst, you obviously need to figure out which countries or regions you need to invest in. Now, the regions that you want to invest in are the regions where you anticipate relatively high economic growth. So how do you figure out which regions will have high economic growth? You can look at past growth numbers, but past numbers are not necessarily an indication of what will happen in the future. So in this section, what we will understand is the various factors that contribute to growth, and as an analyst, you need to be able to understand what is the relative contribution of different factors such as labor, capital, technology, etc. So you need to understand the relative contribution of these different factors, and you need to be able to project what will happen in the future. So understanding the individual contributors to economic growth will make it easier for you to try and predict what will happen in the future. Now let's get into the details. The first basic concept to understand is that of the production function. So here is a very simplistic relationship. Y represents output of a given economy. A is the total factor productivity, also generally interpreted as technology by economists. And then in this simple relationship, we are just showing F, K, comma, L, which means that total output is a function of capital and labor. So we are just taking two inputs here. Later we will see more elaborate production functions that rely on more inputs. Now, a quick word on total factor productivity. This is a number which gives an indication of how productive a given economy is. The higher this number, the more output the economy produces for a given level of factors or a given level of input. Economists generally define technology very broadly, so anything that improves productivity is effectively called technology. Now, let us look at one simple example of a production function, and this example is the Cobb-Douglas production function. And the way this goes is as follows. So according to the Cobb-Douglas formula, the output is equal to A, which is the total factor productivity, and then essentially we are taking this function and blowing it up by saying that output depends on A multiplied by capital to the power of alpha multiplied by labor to the power of 1 minus alpha. Now we need to understand what alpha means. Alpha represents the share of output which is paid by companies to capital. So if the total output is represented by 1, then alpha of 0.7 means that that 70% of the output or 70% of the overall income is allocated to capital. So alpha will be relatively high in developed countries such as Germany. Next point is the concept of labor productivity, which, as the term implies, is simply a measure of how productive your labor is in a given economy. So to derive labor productivity, let us go back to our basic relationship here. So we can say output is equal to total factor productivity multiplied by some function of capital and labor. So if we divide everything by L, what we have is Y over L. So this essentially becomes our labor productivity. It's our output per unit of labor. That is equal to A multiplied by, and then if we divide both K and L, divide both of these by L, then L over L essentially becomes 1. So what we are left with is, let's say small y represents our labor productivity. That is equal to A, which is our technology or our total factor productivity, and then a function of K over L. So let us say that K over L is our capital per unit of labor and comma 1. So essentially this relationship gives us our labor productivity. It is a measure of how much output we produce per unit of labor, and clearly this then depends on the level of technology and the amount of capital that we have per unit of labor. If we look at the Cobb-Douglas relationship over here, then this simply becomes y is equal to A multiplied by K. The small k represents capital per unit of labor raised to the power of alpha. Capital deepening versus technological progress. Here the concept is quite straightforward. We as analysts need to figure out the impact on productivity, which is output per unit of labor. We need to figure out the impact of adding more capital to labor productivity versus the impact of more technology on labor productivity. To understand this, let's look at a very simple production function. So a production function might look something like this. What we are seeing here is that as we add more capital per labor or capital per worker, this is the small k from the previous slide, then our output per worker, this is the y, goes up. But we also have diminishing returns. So as we keep adding capital, initially the increase in productivity will be high, but you can't just keep increasing productivity by adding capital. At some point you will get to a plateau. What about the impact of technology? If you have a situation where you can also improve if you can improve technology, then with the same level of input, so with the same capital per labor, let's say we have 10 units of capital per labor, then you can actually have more output. So what we are saying is that with technology or increase in total factor productivity, the production function shifts up. So then we can have something like this. So this is this is our production function 1 with technology equal to, just pick a number, 6, and if A increases to 7, then we have a new production function which is higher. So if you have a situation where you are moving from point A to point B, the move from point A to point B is due to capital deepening. So you moved from A to B based on more capital per labor. But let's say that a given economy moves from point A to point C. Then we can say that this much improvement, so the improvement from say 100 units of output per labor to 120 units, this is because of capital deepening. And then this distance from here to here, this distance, let's say that this is 125. 5 units of output per labor are coming because of better technology or the increase in total factor productivity. So a summary point here is that if we want a sustained improvement in our productivity or output per worker, then that will only come through improvements in technology, because capital deepening will improve output productivity to an extent, but after that we are essentially flat. So if we want to keep improving our productivity, then that sustainability or the continuous improve in productivity will only come through increases in technology or total factor productivity. Now, having understood these basic points, you need to read example 3 in the curriculum. It's over roughly 1 page and it's a good example. Growth accounting. This is a framework which allows us to analyze the performance of economies, and essentially here is a very basic growth accounting equation. What it shows us is that the percentage change in output is coming from a percentage change in technology, a percentage change in capital multiplied by alpha, and a percentage change in labor multiplied by 1 minus alpha. As we discussed earlier, alpha represents the share of income paid to capital. In the US, it is 0.3, and since alpha is 0.3, 1 minus alpha is 0.7. This is the share of income which is paid to labor. So note that in a sense, alpha is also like elasticity. And what I mean is, imagine that only your capital changes by 1% and technology and labor stay the same. What will be the impact on output? Given that alpha is 0.3 in the US, a 1% change in capital will result in a 0.3% change in output. So essentially, this relationship allows us to determine approximately what happens to output when a given factor changes. Obviously, this expression can be made more elaborate by adding more inputs, but the concept is fairly straightforward. Now, what if labor changes by 1% and everything else stays the same? Then we can see that the total output will change by 0.7%. So bottom line here is that alpha can have two interpretations, or has two meanings. One is it's the share of income paid to capital, and the other interpretation is that it's like elasticity, where a 1% change in capital, everything else staying the same, results in a 0.3% change in output. An alternate method for measuring potential GDP is the labor productivity growth accounting equation, which is given right here. Now, what this equation says is as follows: the growth rate in potential GDP is equal to the long-term growth rate of the labor force plus the long-term growth rate in labor productivity. So you need to memorize this relationship, and you will use it in examples and practice problems at the end of this reading. So again, growth rate in potential GDP comes from long-term growth rate of the labor force plus long-term growth rate in labor productivity. And this is fairly intuitive. So far we've talked about a very simple production function that simply depends on labor and capital. But now we are going to extend the production function and show that the output of an economy can depend on several factors. So here we see that the output depends on total factor productivity, which is similar to what we saw before. And then we are saying that the output is a function of natural resources, labor, human capital, which we will talk about in a short while, capital, which is information technology capital, capital which is non-information technology related, such as machinery, and finally public infrastructure. So the point here is that we can make our production function as complex as we want to reflect the appropriate factors of production. So let's talk about natural resources now. A very basic point that you probably know already is that we have both renewable and non-renewable natural resources. A classic example of a renewable resource would be a forest. Non-renewable natural resource would be oil or gas. Clearly, natural resources are important for growth. So a country that has a lot of land or a lot of oil or other natural resources will find it easier to grow relative to countries that do not have natural resources. However, the curriculum emphasizes that while natural resources are important, they are not necessary for growth. And there are several examples. Take countries such as Saudi Arabia and Venezuela, both very rich in natural resources, but they have achieved subpar growth rates. On the other hand, countries like Japan and South Korea do not have too many natural resources, and yet over the last few decades they have experienced substantial growth. I suggest you read example 4. It is interesting and it's actually a short read, but I don't think it is very testable. Labor supply. The basic point here is that for an economy to grow, one input is labor. So the more labor we have, the more an economy can grow. And when we talk about labor supply in the context of growth, what we are really referring to is aggregate labor hours. So what really matters is the number of hours that are worked in a given period of time. So then, what is it that contributes to increasing the number of hours worked? There are 4 inputs to labor growth. The first is population growth. So obviously, if we have a larger population, then the total aggregate hours worked will likely go up. But the key here is working age population. The next point is labor force participation rate. What this means is that of the working age population, what percentage is actually in the labor force? Next item is net migration. So there are countries such as Canada where the net migration is positive. So obviously, if net more workers are entering an economy, that will help the aggregate hours. And then finally, the average hours worked. So in a given period, such as a month or a year, on average, how much does a worker work? The higher the average hours worked, the higher the overall aggregate hours. We as analysts need to understand the demographics and evaluate how labor input or the total number of hours might change in the future. The sorts of things that we need to look at are as follows. For one, we can look at the percentage of young people entering the workforce. So if you take a country like Turkey, where the percentage of young people entering the workforce is relatively high, then that is a positive sign. If you take a country like Japan, where the percentage of young people entering the workforce is relatively low, that is a negative. Another item you might look at is the female participation rate compared to other countries that are somewhat similar. So if a given country has a low female participation rate, this is the number of working age females who are in the labor force. So if this percentage is relatively low compared to other similar countries, then an analyst might assume that in the future the female participation rate will go up, which will help the labor supply. Again, I would strongly encourage you to read examples 5 and 6. Next, we talk about labor quality, which is essentially human capital. Clearly, if our labor is better educated or better trained, then the output per worker is going to be high. The efficiency of somebody who is well educated and the income that he can generate is obviously more relative to somebody who is not educated. Similarly, with on-the-job training, somebody who is well trained is obviously going to produce more than somebody who is not well trained. So collectively, both education and job training contribute to human capital. Next, capital. Now, when we talk about capital, we need to draw a distinction between ICT, which is sometimes just called IT. This is information, computers, and telecommunications related equipment. So this is one category of capital, and another category then is non-ICT, which is everything else, typically non-residential construction, transport equipment, machinery, etc. So let's look at non-ICT first. So this essentially is our physical capital stock. This capital increases if net investment is positive. So if investment is made, that essentially means that we are investing money in our physical capital. And there is sufficient data which shows a very high correlation between investment and GDP growth rate. So more capital is good, but as we've seen earlier, there is a diminishing returns here. So as we add capital, units of capital per labor, the productivity, total output per units of labor, this goes up, but there is a diminishing returns impact that we need to pay attention to. But nevertheless, more capital means more productivity. In terms of IT or ICT capital, we have seen that this ICT has a very high network externalities effect. The curriculum gives an example of email, where this is a IT oriented tool that has substantially improved the productivity of people. And the more people we have who are using email, the greater the benefit. And whenever you have more benefit with more people, that essentially means that we have high network externalities. This benefit is largely captured in total factor productivity, or essentially greater efficiency. Technology. Now, as we've mentioned earlier, when we talk about technology in an economic context, generally we mean something that is making us more efficient or more productive. So scientific advances, applied R&D, improved management methods, better ways of production, and so on, all these are collectively referred to as technology. When we have technological progress, essentially what we are able to do is produce more output with the same level of input. And when we do that, our total factor productivity, the A, goes up. When A goes up, that means our production function goes up. So as we saw earlier, if we have this production function with better technology, the production function shifts up. For developed countries such as the United States, where we already have a lot of capital per labor, the improvement in per capita GDP comes largely through improvements in technology. So in the US, for example, we might be somewhere here on the capital on the production function. So since there is already a lot of capital per labor, the addition of more capital does not increase productivity too much. So for a country, a developed nation such as the US, to improve productivity, it would rely heavily on better technology. And that's why we notice that there is substantially more investment in R&D in developed countries such as the US. Now let's look at some numbers for Japan and India. So Japan, between 1995 and 2005, the number of hours worked actually went down a little. So can the economy grow even though the number of people or the aggregate hours is going down? Let's take a look. So growth in labor productivity. So this labor productivity refers to the human capital that we talked about. This actually increased, so that's a good thing. That means our people are more educated, better trained, so they are more productive. Growth due to capital deepening. This means that there was more capital that was invested, and that caused or that resulted in some growth. We also had growth in total factor productivity. So our A, which is the total factor productivity, which is already fairly high for Japan, even that went up. Now collectively these items contributed to a 1.1% growth in GDP. The total productivity level in 2010, which is essentially the GDP per hours worked, is very high. It is $40.7. So effectively what that means is that for every hour that a Japanese works on average, the output is worth $40.7. Let's compare this with India now. So in the same period, 1995 to 2005, the aggregate hours worked went up, which makes sense because India's working population at the same time was growing at a faster rate relative to Japan. The growth in labor productivity 4.2%, which again makes sense because there is during this time substantial investment in education and training, so human capital improved. Growth in total factor productivity, the level of technology went up by 1.9%. The growth due to capital deepening, so the growth because of more capital per worker was 2.3%, and all this contributed to an overall growth in GDP of 6.3%. The productivity level, however, is still only 5.3. So for every hour that a worker worked on average in India, the output was only $5.3. So what explains this huge disparity between Japan and India? And essentially there are two or three elements. Probably the items to look at here are that even though these percentages here might look roughly in the same ballpark, but the total factor productivity for Japan already is at a much higher level than India. Actually, the total factor productivity is here. So the total factor productivity for Japan is much higher than that for India. It's growing at a slower rate, but obviously from a much higher level. Probably the level of human capital in Japan is much higher, and the level of regular capital, both ICT and non-ICT in Japan, is probably higher. So those elements explain why the productivity level in Japan is substantially higher than the productivity level in India. And because of that higher productivity, a relatively small country such as Japan still has a GDP that is much larger than India's. Public infrastructure is another huge item where essentially public projects, public infrastructure such as roads, bridges, dams, electric grids, these contribute immensely to the growth of economy, and the public infrastructure projects have huge externalities also. Now take the case of Pakistan, where there is a huge energy crisis, a huge shortage of electricity, and because of that several industries are suffering. If the government can solve the power problem and set up more electric grids, that will have a huge impact across most industries. So proper investment in public infrastructure is essential for the growth of an economy. The curriculum gives a nice summary section, and I will pick the most important element from that section. Essentially, you need to understand the sources of contribution to GDP growth. So I feel that overall in section 4, one of the most important things for you to do is to understand how to use growth accounting. So in this little table, we are using growth accounting to explain where the growth in GDP is coming from. So take a country like the United States. In 1995 to 2005, growth in GDP was 3.3%. Where did this come from? 0.6% came because of labor quantity. Labor quality, so better education, better training, that contributed to 0.3% growth. Non-ICT capital contributed to 0.7%. ICT capital contributed to 0.8% of this number. Then total factor productivity is really a plug. What I mean by that is we can establish through available data that growth in GDP was 3.3%. All these numbers are also established based on available data. It is impossible or extremely difficult to measure total factor productivity. So what we essentially do is figure out this 0.9 by doing 3.3 minus all these items. So in other words, whatever part of the growth cannot be explained by these factors is then attributed to total factor productivity. Let's also look at India over the same period. India grew at a reasonable rate of 6.3%. Where did this growth come from? It came from labor quantity, labor quality. So labor quality did not improve too much. Non-ICT capital, this was a pretty major area. So we can see that in this period a fair amount of investment was made, and then in the subsequent period there was even more investment in capital. Also, some contribution came because of information technology related capital, and total factor productivity contributed to 1.9% of this number. And again, the 1.9% is a plug. We did 6.3 minus all these numbers, and essentially we can then say that 1.9% of the 6.3 came because of better technology or better productivity. Examples 8 and 9 I think are essential from an exam perspective because they apply many of the concepts that we have learnt in this section. So make sure you spend a lot of time on these examples and do them well.